So why is total order broadcast important? And the short answer is that it facilitates implementing fault-tolerant services. To understand why, imagine how we would make an arbitrary service fault-tolerant. So the first thing probably that comes to mind is that we will replicate the service state in multiple places or at multiple processes. So once we have done that, we can use a reliable broadcast or one of the variants of reliable broadcast to disseminate updates or requests that manipulate the service state. However, if we don't have total order for or total order guarantee for this reliable broadcast that we use, then updates issued concurrently by multiple clients may cause the states of different replicas to diverge. Okay, and that would basically render our service unusable. So with total order, we won't have this situation. And to be more precise, I would like to introduce this paradigm, which is called state machine replication, or SMR. And this paradigm provides a generic recipe for making an arbitrary service fault-tolerant through replication. So just one remark on the terminology. So state machine replication, also sometimes referred as replicated state machine or RSM. So you may encounter both these terms in different places. Okay, so now let's discuss what state machine replication is. So in state machine replication approach, we model a service as a deterministic state machine. So what is a state? So we already know that. So state is generally speaking a map from variables, from variable names to their values. So in addition to that, in a state machine we also have commands. So these commands are deterministic programs. So this is why it is a deterministic state machine. So one example of such commands can be transactions. So like multiple operations that need to be executed atomically. So what commands do, they transform a state, the state of the service to another state, and as a side effect they may produce an output or return a value. So important observation is that determinism, so the commands are deterministic and the state machine is deterministic, implies that the outputs of the state machine are entirely determined by the initial state of the state machine and the sequence of command that has been executed. Okay, so so this is the state machine definition, and to make state machine fault tolerant, we will replicate it on multiple processes and then use total order or atomic broadcast to disseminate the client commands. Then we will make sure that we apply the commands in the order that they are delivered by the total order broadcast layer. And that will ensure that every state machine will execute the same sequence of commands, and therefore, by the definition of state machine, they will all produce the same sequence of outputs, and they also have consistent states. Okay, so this is a state machine replication. So let's see an example. So the example we will consider has to do with reserving seat for airlines. So it's an airline seat reservation service. So the state in this case is a mapping from the seat identifiers, which consist of a row number and the seat number, to this set. So it can be either, the seat can be either free or it can be reserved. And if it is reserved, then it also has the name of the person who reserved the seat. Okay, so state maps seats to this set, which can be either free or this tuple of reserved and the name of the person who reserved. So here are some examples of seat 1A is free and seat 2B is reserved by Alice, and so on and so forth. So the initial state of the state machine is that all seats are free. So all seat identifiers are mapped to the atom free. So the command supported by the state machine in this example is the command reserve. And reserve takes two parameters, a seat identifier and the name of the person who is trying to reserve the seat. And the command is a program which looks like this. Okay, so if the seat ID associated with the command is free according to the current state, according to the seat map, then we reserve this seat, so we assign the name of the person reserving to the value of the seat ID. Okay, and we return OK in this case. Okay, so in this case the output of the state machine is OK. Otherwise we return this atom occupied. Okay, so this is a simple specification of airline seat reservation service as a state machine. So let's see an example. So in this example we don't have replication, so the service is implemented by a single process or a single server, for example. Okay, so this is the map of the seats, so all seats are initially available. So now we have a request from Alice to reserve the seat 3E. So seat 3E is currently free, so this request is granted and Alice is assigned to the seat 3E, and the output is OK. So now another user, Bob, is trying to reserve 6F, and again 6F is free, so Bob succeeds, gets it reserved and gets OK back. Now suppose Charlie is trying to reserve 3E, but 3E is occupied by Alice, and for that reason Charlie's request gets rejected and it gets occupied response back. Okay, so this looks simple, but the problem of course is that in this case the implementation relies on a single process or single server, and therefore if this server crashes, then the service becomes unavailable. So any further request can't proceed before the service is restored. Okay, so without replication we don't have fault tolerance, so we don't have availability for our services. So now let's fix the situation. Now let's replicate this service. So here we have 3 replicas, and we are going to use broadcast to disseminate reservation requests. So now if we don't use total order, then the following situation is possible. So both Bob and Alice are trying to concurrently reserve seats, and if they try to concurrently reserve the same seats, which is 3E, then some of the replicas will get the like this replica here will get Bob's request first and will assign 3E to Bob, and this replica will get Alice's request first, and they assign 3e to Alice, and as a result, so both of them, they won't notice that anything is wrong, so they will get OK for their respective requests, and as a result, they will both come for this flight and discover that the seat is actually overbooked. Okay, so obviously the total order that won't happen, and this is because one of the requests, so in this example Alice's request, gets to everyone first, so and for that reason Alice will succeed to reserve the seat 3e, and Bob will get a response occupied to his request and won't be able to reserve this seat. And also in this case the state, the reservation state or a seat map at all replicas is consistent. Okay, and so if any one of them crashes or disappears, then the other two will basically be able to operate from the point at which crash occurred. Okay, and this is because their state is consistent with the crashed replica and between themselves. Okay, so this is an example. So let's now